Loci. So please welcome Moshe Gur.
Thank you for the introduction. This is an official title, but having spent now a few days in here, I'm overwhelmed by several aspects. One of them is the easy problem versus the hard problem. And what sort of surprised me is that it seems that most people are convinced that the easy problem is really easy. In a matter of a few years, it will be all solved, maybe using your iPhone or iPad or whatever, you have it. It is nice people are optimistic. 60 years of failures are nothing to us. So I would like to throw some doubt on the easiness of the easy problem. And so alternative title is on the unity of perception. How does it come about? And you see below Lashley's way of putting it many, many years ago. So the conventional view, which I call the machine hypothesis, is if we have 2 points in space, and in order to compare them, to integrate or to process, we have to, the machine or computer or the brain must bring the information into a common locus, to a comparator, register, what have you. Otherwise, we don't know how to do it. So naturally, that is how we think about the brain. And an example from the visual system, how do we perceive and understand and recognize object, is by hierarchical process where things are continuously converging from simple units that are here in V1, they go later on to a more complex representation in V4, even more complex, larger receptive field in the IT and the prefrontal cortex. So converging and converging and converging until somehow you get to the decision or to recognition or whatever locus. This is repeated in many aspects here from functional MRI people who show hierarchy. At the bottom of the hierarchy is V1, then climbing up. And you see there's sort of a staircase even here if you're not convinced of the hierarchy, it's really pictorially like staircase. You're climbing up from the low rungs into the upper part of the hierarchy until you get to these very interesting areas where all the action is. And of course, we understanding even more complex operation like emotion. Again, you see these arrows all over the place. Things are converging from here and there into some locus. Even in models like oscillating network, the famous gamma frequency and so on, you can see that the network is collecting information from different loci and then brings them into a common one. So A's down here are connected into A up here and so on. So even when you talk about interacting dynamic network, they work by convergence. And below another model by Abeles, also Sinfire, again, to decide between T and L, you have to converge. One convergence gives you T, one convergence gives you L, so everything is fine. I'm here to suggest an alternative hypothesis where the brain can compare inputs that are separate in space, but not in time. So is it possible? Can we really reject one hypothesis or make it less appealing and look at the alternative one where the brain can compare between 2 different locations, but events that occur more or less simultaneously? So the research is how well can the brain compare localized stimuli, and a corollary does this comparison depend on cortical distance, and we can use different distances, of course, few millimeters, few centimeters. So what is the paradigm? I presented few stimuli, different location, which we know are in primary visual or somatosensory or auditory cortex. I looked for the simplest experiment possible, for the simplest stimuli possible, so we won't get bogged down by all this fancy discussion, object recognition, grandmother cells, and what have you. But very, very simple, very elementary in 3 modalities, and detecting stimulus I want to say asynchrony, namely time interval, and detecting different spatial organization. And experiments are mainly using one hemisphere, but as a control, I also use two hemispheres, and I also looked at the ability to detect the gap in one locus. Okay, the first experiment I'll explain a bit, and all the other experiments are of the same format. So once we understand this, everything else is very easy to detect. So what we see here is in the somatosensory cortex, I put the first one I put, oh, come on. I put two speakers that gives you a vibration on one on the thumb and one on any other finger that you see down here on the other four fingers, on the wrist, on the forearm. And the stimulus was either contiguous, I mean, we have few vibrations here, immediately few vibrations here, or we have some delta time, namely a set of very short, 8 millisecond vibration, delta t, and then another 8 milliseconds. It's subjected to say whether it was contiguous in time, it didn't detect any gap, or it did detect a gap. I'll come to the other configuration in a second. So what we see here is rather interesting and rather surprising that the subject were able to detect a very, very small gap in time of few milliseconds, about 4 milliseconds, in a somatosensory, which is not supposed to be so sensitive, but it did, and it didn't matter even if you went to different fingers or even up to the wrist, which is about 4 centimeters in cortical space. The ability to detect was about the same. Only when we went to the forearm, there was some increase in about 1 or so milliseconds in time. As a control, as I said, we looked at stimulate to two hemispheres, namely two hemispheres, and it was completely different. The time doubled, perception was weird, it was much harder to do the task. On the other hand, when we did it in one location, just look for time interval through one channel, not two channels, it was about the same. All right, other experiments follow the same pattern. So I did it in the auditory when one ear, you're using one ear, we hear two tones, which are one frequency and then higher frequencies are contiguous in time, and then there's a difference in time between them. So it's a harder task because not only we hear two different tones, tone changes from low to little higher, it also, sometimes there's an interval between, sometimes there is none. Yet the subjects are able to do it, and you do it very well. Of course, as we go to higher and higher tone compared to the basic 250 hertz tone, it becomes more difficult because you have low tone switching to very high tone. Yet they can do it again in few milliseconds, less than 4 milliseconds. Only when we go to the higher tone, it increases somewhat. Of course, if we do it in one tone, just detect an interval, a disturbance to one tone, then it's about 1 millisecond here. Again, if we go to two hemispheres, it's much worse, and perception is much different. All right, so this is somatosensory, auditory. For the visual, I have to tell you something. It's so trivial, but it may come as a surprise, because we haven't thought about it. I say we, I'm included, that unlike color or sound, which are qualia, space perception is not. Space is reconstructed in early visual cortex. So it is not, we don't take something outside and turn it into, by some action into something else. Color is not wavelengths, it's correlated. But it's not. We don't have any idea about wavelengths, we see colors. But not so in space. In space, we see the space that is outside with certain constraints, of course, but we see it being reconstructed. This has been known for almost 100 years, but I think all of us fail to see the significance in it. So this is, don't do it to me again. This is from Holmes, and how the visual world is mapped onto the striate cortex here, more modern one by Horton and Hoyt. And you see that this very, very small spaces, the first 2.5 degrees of eccentricity is mapped into a fairly large cortical space. So there is a space is reconstructed. That's what we mean by a map, by a topographical map in V1. All right, so then I did a visual experiment, put two LEDs in different position in visual space, fixating down here, and then two position in primary visual cortex are being stimulated, and we have to check to see one time two are being turned on simultaneously, and then another time there's a small gap in time, and the subject has to say whether they are continuous at the same time or there is some gap. And as long as we are within the fovea, you see there's there's no differences between positions. We'll be able to detect about 15 or so millisecond gap. As we move outside the central fovea, it becomes a little more difficult. And there, when we look at two hemispheres, it also becomes much more difficult. This is a special case, which I'm not going to talk about, maybe foveal sparing, but I'll leave it for now. And if we do it in a single channel, let me just look for flicker, under those conditions, it is much worse. So it is actually easier to compare two positions in space than to compare interval in one position in space in the visual system. OK, next I move to another task where there were two squares now can be turned on and off together, or one would be turned off slightly earlier. And this gives a different sensation. I won't go into it, but there was no sense of motion, just one is shorter than the other. And again, quite similar and even more dramatic when you look at two hemispheres. It's simply almost impossible to do the task, but you can actually still do it. And look, you could do it at 8 degrees of eccentricity, which is fairly impressive. So you can go up to 4 or 5 centimeters in visual cortex and still compare across it in a fairly good, consistent way. Other type of experiment in space are comparing angle, namely are the 2 points on a straight line or are they on an angle? And actually, and you see if we go to up to 6 degrees, no problem doing it, and we can detect an angle of less than 2 degrees, which is fairly impressive, but again, consistent. We can do it. We can relate these 2 points in space. Absolutely no problem. We can do a different task, and we can compare distance between these 2 points to these 2 points. Again, we can do it up to 3, 4 degrees. Again, if we do it in two hemispheres, it becomes much worse, but we can relate, again, part of a degree. We can, in space, we can do it. And I'm not going to to show you any more. We've done enough. But I did the same type of experiment with comparing size, and did it with a 2-tier or double-tier experiment, and you'll see why in a second, which the subject has to say, are the simple here and here the same? If they are, go ahead and compare the distance. If they are not, just ignore. OK, and this can be done as well. OK, so to summarize, in 3 modalities across considerable distance within one hemisphere, the brain can compare localized stimuli extremely well. Comparison is performed while keeping the identity and localization in space or time of the elementary stimuli. In all 3 modalities, across a considerable distance within one hemisphere, cortical distance has no effect on interval or spatial discrimination. Even at the exact same location, interval discrimination, although easy, was not very different. Now, when conduction was required between hemispheres, performance deteriorated significantly. OK, so how do we explain it? We have a set of data, very simple experiment, very clear results. How do we explain it? How does the brain compare between two locations in cortical space? The machine hypothesis would say, OK, we must have the data, the information, or the stimuli coming from primary cortex, primary auditory, visual, or somatosensory, goes on through topographic or to tonotopic or organized area, but they are topographic, so the information is still not combined. Into some area, somewhere downstream, it is the integrating area, which has many cells that can compare between 1 and 2, 1 and 3, 1 and 4, etc. That is how a machine would do it, that how a computer would do it, that how the brain supposedly does it. Take an example from the auditory. So we have different frequencies that we compare between in primary cortex, and it goes to somewhere which can compare all those frequencies to tell us whether there was an interval or was no interval. That's how it should be done. This peculiar experiment I did to show you what is involved, this is a very simple experiment, really. You know, are simple the same? Yes, go on. Not, go to the next one. No big deal. But if you want to explain it in the way conventional wisdom does, look what it involves. In V1, we need orientation selective cell, maybe 3 of them, to represent a triangle, maybe 10 of them to represent a circle, and that's only the first step. Now it should go to V4 probably. There will be a triangle cell, and then there'll be a circle cell. And I'm asking as an aside, are the cells for every shape, or even arbitrary shape? I don't know, but that's what it should be. And then you compare somewhere in the cortex. Should be an area that compares the shape and makes a decision. If different, ignore. Not, it's the same. Then you allow a comparison. So very simple experiment, very complex machinery. But let me push on. The experiment I did, I compared spot 1 or dot 1, area 1, with 2 or with 3 or with 4, etc. I went up to 8, but you can, let's say, take 11, so it'll be a nice number. So if we look at all the possibility, 1 and 2 and so on, and 2 and 3 and so on, and 3 and 4 and so on, we have 55 possible interaction, only using 11 localized spots in primary, say, visual cortex. But if we look at the ability to discriminate in visual cortex, I made sure that at 1 degree you discriminate easily those many points. At 2 degrees you can discriminate those many points. And this is only 2 degrees. If we go to 5, there'll be at least, and this is very conservative, 1,000 separable loci in the 5 degree. And if you look at all the possibility of 1 versus everyone else, 2 versus everyone else, and so on, there can be 500,000 possible interaction. But wait, I'm going on. There can be various tasks, I mean, between any 2 points. I mean, I showed you different 2 tasks in time, space, 2 versus 1, 2 versus 2, area versus area. It can be space and compare shape and then compare distance. There can be many types of arrangement, 1 versus 1, 2 versus 1, 4 and 5, and you know, you can use your imagination. We don't need it just to compare 2 loci. We can compare more, maybe what's happening in 2 compared to 1, in 4 or 5. I don't know how many you can do it. And of course, shapes, as many as you like. I use dots, I use squares, I use triangle, but why not use something else? So, yeah, of course, you see where I'm going at, too. So if I use very conservative estimate, we have 500,000 possible interaction times maybe, I mean, a very small number, 10 different tasks and different arrangement, 10 different shapes, 5 different locus arrangement, and then all in all, I get to a very big number. It's 2.5 billion possible interaction. Now, can there be a cell somewhere downstream from V1 for every possible interaction? Can population code come to the rescue? Well, I say no. Population code says, you have so many possibilities. Population here would code this, and another population overlapping with the first one can code something else, another, and we can have infinite number of overlapping partial population of the whole population. This has been very popular, you know, expert cells, phase cells are those kind of cells, or this kind of model. But if we think about how it is being decoded, if you take all those cells and then send them somewhere else to tell the brain all those responses mean face A, or those responses mean face B, then you are converging it again into a target. So we have done nothing. If you tell me that the brain can integrate over different cells, or the brain can integrate over different positions in space, so we are back to the alternative hypothesis. So this is not a rescue. So let's sum up. Can the experimental results support the machine hypothesis? Looking at time, can an area of 4 or 5 synapses from primary cortex can discriminate 3 millisecond interval? I say unlikely, because there's going to be a delay. As you go from one area to the other, you add maybe 10 milliseconds each area, you go 4 or 5 areas, you end up with 50 millisecond increase. So given 70, 80 milliseconds from the outside, it's very hard to think that you can have 3 or 4 millisecond discrimination. Can be discriminated in different positions in time, or again, the order of 3 or 4 milliseconds. Again, you have different paths, and it's unlikely that short paths and long paths would give you the same discrimination. And again, when you do it with a single channel, there is no need to get 2 channels to converge. You get more or less the same results. So the brain can compare 2 points in space and 1 point in space, more or less at the same ability. Now, as a space, what are the space considerations? Can be cell downstream that support kind of information. So unlikely. We saw the astronomical possible configuration. The unlikely there are that many cells. Actually, we know that there are no such cells because downstream receptor fields are larger, so cells combine and look for larger stimuli that could not really respond to very, very small stimuli located at a very, very discrete position. And when we look at 2 hemispheres, when the brain has to use wires to communicate between 2 hemispheres, then everything deteriorates considerably. So conclusion is it's impossible to accept the machine hypothesis. And now I go to this famous philosopher and scientist, Arthur Conan Doyle, who said that once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. So this is my position. I cannot see that the conventional machine hypothesis can work in the brain, so we must turn elsewhere for a solution. So the alternative hypothesis actually was brought up by Charles Sherrington many, many years ago, was ignored, but that's what he said. So the brain does not work like any physical device. It does not have to bring the information to a common position, but it can integrate over space. Other phenomena up to now are not explained. Face perception, face recognition, a multisensory phenomena, integration. We see a face, we see it in all its wonderful detail, we hear it in all wonderful detail. Where the 2 detailed information come together? There's no third area in the brain when the 2 come together, so we cannot explain many, many phenomena. Let's go, before I finish, to look closely at object recognition as an example. Again, this is what I showed you before, that it is done by convergence to expert cells, but let's say how the wireless hypothesis works better here. So to recognize an object, we need to distinguish it from other objects and to disregard change. Namely, we know that it is an object even though it is smaller or tilted and so on, the invariance. So when we see an object, we retain its identity. We see each point of the object in where it should be, and yet we also see the object as a whole. A nice experiment years ago that we took, took a stimulus in visual space and projected it, and a monkey looked at it, and the monkey's brain shows a duplication, what I call the reconstruction on the monkey's brain. So a line in space is a line on the monkey's brain. A dot in space is a dot in the monkey's brain. So when we see a dot or we see a line, there's a line of activity or dot of activity in V1. When we see a phase, there's the phase pattern in V1. But what about the classical oriented cells or complex cells in V4? What about phase selective cells? They did are convergent cells. They reflect convergent from lower area, but they are necessary for global characterization. Is the object near or far, or is the face on a rose? So when the object is perceived, the activity in many visual areas, detailed reconstruction in V1, information about size and so on in other visual and non-visual area. So there's pattern in many, many areas, and the simultaneous existence of those patterns in different brain positions allow us to see an object because they appear there in time. I'm winding down. So if not by convergence, how can the brain integrate wirelessly? Of course, I have no answer, but we have to consider alternative. Are there macro-physical forces of field, like electromagnetic fields? Do we have to call QM to the rescue? Or do we have to consider that there are physical forces which we are not aware of yet? I leave it open, of course. And so implication, and I'm finishing, to understand the neural events giving rise to perception, we have to abandon the machine hypothesis and accept that the brain can, at times, integrate wirelessly across cortical space. Computers cannot simulate, emulate, or replace the brain. I'm sorry if it hurts somebody, but I think that's what it is. The easy problem is not easy, and it's not going to be solved anytime soon. Accepting the wireless hypothesis may lead to a better understanding of the issues behind the easy problem and may also contribute to a better understanding of the hard problem. Thank you.
Okay, we have some time for questions. Stu?
Thank you. That was really great. Well, I'm a big proponent of quantum mechanics in the brain, so I find this very, very good. But let me be conservative for a moment and ask, are there gap junctions laterally connecting these areas? Because that would at least give you synchrony and the possibility of electromagnetic interactions.
Well, in V1, there's, of course, if you have gaps that connect across V1, then you lose topography and you lose identity. So that's why a discrete point in space is stimulating discrete point in V1. And the synchrony, there are two quick answers. First, some of the stimuli would not even elicit synchrony. I mean, you have 8 millisecond, even 4 millisecond stimulus, you have a gap in time, and there are another stimulus. So this stimulus is not there anymore. To have synchrony, you need a much longer time, a few tenths of a millisecond to do it. But even synchrony tells you that this point in space and this point in space, this point in space belong to each other. They form an object compared to the background. That's not going to solve this problem.
Well, if you have gap junctions, though, you have a continuous space, and you could have electromagnetic or quantum effects in one topology.
Maybe, maybe.
What about something like reverse hierarchical theory in RHD, Ullmann, Achisa, meaning that where a stimulus, two stimuli will go from V1 to V4, maybe higher upstream, but there's also downward signals, and the whole thing only stabilizes after something happens between the different levels, but there's some kind of a backward reaction.
Yeah, again, it's, the idea is that what the core of, in the convergence, in the conventional way, the core is bottom up. Now you have top down, which helps you select, helps you modulate, and stuff like that, like the Achisa-Hochstein idea of concurrent stream. But the basics, first you have convergence going upstream, and then downstream do something else, but they do not determine the object. They cannot, actually, even according to those theories.
So it seems like two things there. The first is, in your model of vision, you're assuming that the intermediate representations are, that the intermediate representations, such as middle level vision, are discarding the information that the higher level vision would need to solve the matching problem. So I'm wondering why you're making that assumption. And then it also seems like your data about the comparing across different sides of the visual field, going through the corpus callosum being slow, would be an argument in favor of the fact that the connections are being used, because the connection path.
Comparing across the visual field or visual cortex operation?
I thought you compared left and right visual field and found that the reaction time, that the task could not be done.
So I can't. I can't hear you well.
Oh, okay.
We'll talk later. Okay.
Okay, we can talk later.
Okay.
Yeah. Oh, I'll try one more time. So didn't you compare left and right visual field stimuli, and that did not work? It only worked when it was in the same visual field?
Yes, I on purpose, of course, I compared what happens when you have, oh, sorry. I put stimuli in two visual fields, so it affected two hemispheres. And I asked to compare. I did it somatosensory, auditory, and visual. And it's much worse as far as time or ability to do it, double or even treble. Also, perception is very different. While you do it in one hemisphere, you get a unified concept. When you do it in two hemispheres, then you have some cognitive effects. Is it there? Is it not there? Is there an echo? I mean, you start thinking about it. It does not come as a unified percept. So when you use wires, the result is much, much different. That was my point.
But if you are arguing for non-local communication, that could happen across hemispheres.
Yeah, I argue that for non-local, I mean, there are times, of course, I mean, the brain uses axons, I mean, no doubt, for many, many things. Okay, there are occasions where it does not. And these are, I think, the interesting occasions.
Perhaps I misunderstood you, but basically I thought you were basically saying one of the arguments for your theory is that, through combinatorial explosion of the various possibilities, you couldn't have enough higher level nodes to basically construct the representation. But if you use hierarchical invariant representation, basically you can have a much smaller number of top level nodes that in conjunction with their lower level nodes can represent very large combinatorial explosion of possibilities.
I don't know. You have to give me a mechanism. What I describe, you have many, many points in space which are very localized and very small, and they have to be compared. Now, when you talk about high mechanism, I have to say that your question echoes what most people do. They just tell me high-level, low-level interaction without even giving me a block diagram. How do they think it can happen? You can have 2 points here and 2 points here, and you compare them. What gets to the high level? What kind of information goes to the high level? How do you preserve the spatial identity and the spatial relationship and the task interaction at some high level? I mean, maybe you're right. I cannot conceive of such a mechanism.
Well,
that's why I went to those detailed information.
Just a simple way. Say, for example, as you go up higher in the hierarchy, you're representing larger rectangles of associated lower level symbols going down a hierarchy. Then basically you could basically say these two things are being activated in the same unit. It might be the top level unit. And then if you could keep alive the track down through the hierarchy, you would in total be representing the information you're interested in.
Well, the short answer is you're talking now about information. You don't talk about representation. The true representation exists, in V1. When you start converging to higher and higher and higher triangle, this is not what the stimulus looks like. This is now information about the stimulus. There is a triangle somewhere there, but you lost the identity. You lost the spatial identity. We can talk about it.
Okay, thank you very much.